Good evening. We are starting on lecture number 19 of Power Electronics and EV Drives course. In today's class, we are going to start on induction motor drives and synchronous motor drives. As I mentioned in the last class, the induction motor drive as well as synchronous motor drive, both of them have the same kind of stator structure. So you are going to have basically in the stator, three-phase space distributed winding. And it is going to be supplied with three-phase time distributed currents. This is what is going to be the basic structure of the stator as far as both synchronous motor, three-phase synchronous motor and three-phase induction motor are concerned. So what we have got here, for example, it is going to be somewhat like this. So let us say I have A here and A dash here. So I'm going to have, let us say, A is carrying current coming out of the board and B is A dash is carrying the current which is flowing into the board, which means this is the return current and this is going to be the forward current. And we are going to have again B somewhere here, which is 120 degree shifted. And we are going to have B dash somewhere here. So let us say this is B, which is actually carrying the current of B phase that is coming out of the board. And this is B dash, which is going into the board. And we are going to have the third phase, which is actually here, which is C, and this is going to be C dash. So C is again C phase current that is being carried into the board or out of the board, and this is actually carrying the return current. Okay. And although we have shown A and A dash as though it is just occupying only one slot, as we said in the last class, we are going to have something like this as the stator structure. So it is going to have the slots somewhat like this. The slots are carved in the inner periphery of the stator. So the stator is made up of again iron, and it is going to have multiple stampings which are stacked together to make the entire cylinder. So this is going to be stacked together to make the entire cylinder. And in these slots, we are going to have, let us say, A phase winding, and these are going to be maybe A dash. And similarly, we will have B here and maybe B dash on this side. And we are going to have probably C here and C dash on other side. So this is the way it is going to be. And if we actually look at ideal machine, the winding should be sinusoidally distributed. What we mean by this, actually what we mean by winding should be sinusoidally distributed. If we look at it, if I say that this is theta equal to 0 degree, so cos theta is 1. So the maximum number of A phase windings should exist here, which are carrying current in one direction, and the maximum number of A phase windings should exist here exactly at 180 degrees opposite, which are carrying the return current or the current in the opposite direction. Similarly, if I look at 120 degrees displacement, this is theta equal to 120. At this point, B phase should have maximum number of conductors carrying the current in forward direction. And here, that is 120 plus 180, around 300 degrees or something, we should have B phase windings which are carrying current maximum number of conductors carrying current in the opposite sense. Similar is the case with respect to C phase also. Okay. So I should have at theta equal to 0, cos theta corresponding to cos theta, the maximum number of conductors, if I say, is n. So as you come towards 90 degrees, where cos 90, this is cos of 90 degrees, theta is 90 degrees, the number of conductors should be minimum as far as A phase is concerned. That is, it has to be literally 0. So if this has to be followed, I should have had infinite number of slots along these, periphery, inner periphery of the stator. And I should have had maximum number of conductors along theta equal to 0. And as I come towards either theta equal to 90 or theta equal to minus 90, I should be having literally 0 conductors. And all in between, I should have like cos 60 is half, so n by 2 conductors should be there when theta equal to 60 and so on. So I should have essentially the conductors, sinusoidally or cosinusoidally distributed. And one more thing I can say is, let me probably stop talking about three-phase conductors now. Let me just talk only with respect to one single phase. So if I am talking about one single phase, if this is A and this is going to be A dash, as per thumb rule, I should have actually the MMF or the flux directed in this particular manner. So FA should be along this. So if I am talking about the current that is flowing in A and A dash, or that is the forward current and the return current, they are at its maximum value. So let me show that current which is sinusoidal in nature, something like this. Okay, so this is the current. So if I am talking about the instant which is corresponding to, say, T naught. So at T naught, when I am looking at the flux that is created, I should have corresponding to whatever is the current here. If I may call this as IM, that is the maximum current. So N times IM is the MMF at this point in time. So I should see that along the FA axis, I will have maximum flux, and I should have minimum flux here as well as here. So I should actually, if I try to look at this as theta equal to 0 degrees, for example, or theta, instead of theta, let me take this as phi equal to 0 degrees. So I should say, if I try to draw how the MMF would be as you go along this way, I should show as though this is the maximum MMF that I'm getting, and it should be somewhat like this. So this is phi angle with respect to phi. So with respect to space, I am drawing what is FA, how the magnitude of FA is. So FA is maximum at phi equal to 0. And as I go towards this, when phi equal to 90, it becomes 0. And when phi becomes 180, it becomes maximum in the opposite direction. And at phi equal to 270 or so, it is going to be literally 0. And then it is going to reach the peak again, positive peak again at 360 degrees. So this is going to be 360 degrees. So this is the MMF distribution with respect to space, spatial distribution. Whereas this is the current distribution with respect to time, how the current is oscillating with respect to time. So let me again draw this current as though this is the way it is going to be. So this is the current distribution with respect to time. If I try to look at this at t equal to t1, for example. So at t equal to t1, probably I'm going to have the current which is, a little less than Im. If I say this is 90 degrees, Whereas at T1, omega T is maybe 90 plus 45, 135 degrees. So this is going to be Im divided by root 2. That is going to be the current at this point because this is 135 degrees. I'm talking about this as 135 degrees. So in that case, if I try to look at what would be the MMF distribution with respect to phi, I should draw it as though this was corresponding to n times Im. Now this will be n times Im divided by root 2. So I should probably have it somewhat like this. So it is essentially again sinusoidally distributed, but it is going to be somewhat like this with the peak being Nim divided by root 2. So as time goes by further and further, at time t equal to t2, the MMF will be completely zero. If I try to look at it at time t equal to t4, it should be exactly reversed. So I should have minus Im coming here and plus Im going here, and it should go like this. And when I look at T5, which is again another 45 degrees from T4, then I should have this coming down somewhat like this. It will be probably again Im divided by root 2, but exactly in the opposite sense. So when I am looking at a single phase sinusoidal time distributed current feeding a single phase winding, I will have a pulsating magnetic flux. It is not traveling, it is standing wave. It will be a standing wave. Only thing is, you are going to have variation in the magnitude right from n times Im to n minus n times Im, and it is traversing all the in-between values. The zero where it occurs, that will not change. Here also the zero will not change. So what we get is a standing wave, but that is pulsating in nature. Whereas when you have a three-phase winding and it is fed by three-phase distributed, time distributed current, that's what happens in a three-phase machine. So under such a condition, what happens? That's what we are going to see. So what we have got here is a stator, which is common to either induction machine or synchronous machine. And these three phases are going to be fed with three-phase time distributed current. So this is one phase. This is going to be the second phase, what I'm going to draw. So this is the second phase, and I'm going to have the third phase going somewhat like this. So this is the way it is going to be. Okay. So let me call this as IA, this as IB, and this as IC. And if I'm writing IA equal to Im sine omega t or cosine omega t, IB will be Im sine omega t minus 2 pi by 3 or 120, and IC will be Im sine omega t plus 2 pi by 3. This is the way the three-phase currents are going to be. Okay. Now this is omega t axis. What I have shown here is omega t axis. So MMF or flux corresponding to the magnetic field or magnetic flux corresponding to A phase is always going to be along this axis. This is how FA will be. I'm showing the magnetic field of A phase in space, that will be along FA. Whereas if I try to look at what is the magnetic field corresponding to B phase, that is going to be exactly 120 degrees away from FA. So this is going to be FB, and FC is going to be along this. And please note, I have shown as though FB is leading FA by 120 degrees because this is 120 degrees. That's what we said. and FB is leading FA by 120 degrees. I have deliberately shown it this way because if it is like a generator or even a synchronous machine or whatever, I am going to have the North Pole and South Pole like this. And normal direction of rotation is going to be anti-clockwise. So this North Pole and South Pole North Pole will face A first, and only when it rotates by 120 degrees, it will face B. Then when it rotates further by 120 degrees, it will face C. So which conductor it is actually encountering first? It is encountering A first, then comes B, then comes C. So that is why I have placed the conductors like this. So that first comes A, after 120 degrees comes B, and another 120 degrees, after which C comes. Okay. Now let us try to look at a point which is corresponding to again t equal to t naught. Then I'm going to look at what happens at t equal to t1, and let me look at what happens at this point which is corresponding to t equal to t2. So these are the 3 points I'm going to look at. So at t equal to t naught, I am having IA, whatever is the current in A phase, that is going to be Im, the maximum value of current. At that point, if I try to look at what is IB corresponds to from zero crossing, it is about 30 degree before. And here C is concerned from this zero crossing. From this zero crossing, it is actually 30 degree away, but both are in negative direction. So I should be able to say IB will be Im sine 30, but with the minus sign. So it will be Im divided by 2, and IC will also be Im divided by 2. That is what it is going to be. Okay. And both these are in the reverse direction. So I am writing this as minus of Im by 2. Now, if I try to draw exactly how the MMFs are going to be, as far as FA is concerned, let us say I am drawing it like this. So this is corresponding to some N times Im, assuming that all 3 phases have equal number of turns. The maximum number of turns is N. So I'm going to write N times Im corresponds to whatever is the MMF corresponding to FA. And for FB and FC, it should be N times Im divided by 2 and N times Im by 2 with a negative sign. So if it had been positive, FC would have been in this direction. But because it is negative, I have to just draw this with 180 degree shift. So this is going to be N Im divided by 2. The same way here, I'm going to have this as N Im divided by 2. So the length has to be exactly half of whatever I'm looking at. And here the angle has to be 60 degrees. The same thing holds good for this also. When I vectorially add, so this is FC and this is going to be FB. When I add them vectorially, I am going to have, this is going to be NIM plus NIM divided by 2 cos 60 plus NIM divided by 2 cos 60. This is what is going to be the resultant, which is coming along this direction itself. So it is going to come along this direction, and cos 60 is half. So because of which it will be NIM divided by 2 multiplied by half, and NIM divided by 2 multiplied by half. So the total is going to be 3 by 2 NIM. So I should say under this condition, the resultant MMF or resultant flux is going to be 3 by 2 NIM. And along, if I may call this as theta equal to 0, this is going to be along theta equal to 0 degrees. Now let me try to check what happens at t equal to t1. So let me try to write that at t equal to t1, right? I am going to have again, if I try to look at T1, this is the point at which I am looking at T1. So this is exactly about 30 degrees away from the peak point. So this will be equal to sine of 120. So I should say I of A will be sine 120, which is root 3 divided by 2 Im. And IB at this point is 0. So IB is 0. Whereas IC, if I try to look at it, so I have to say it is on the other side. And it is going to be minus root 3 divided by 2 Im. Okay. So in which case, I should be again able to draw similar vector location of FA, FB and FC. So FA is going to be along this same normal direction of, um, A phase MMF. So let me draw this once again. This is what is going to be root 3 divided by 2 Im, which is FA. And FB is 0, there is nothing that is available. And FC, FC we already drew in this direction with the negative current. So we are going to have FC again along this. So this is also going to be root 3 divided by 2 Im, and this corresponds to FC. Now, if I add these two as per parallelogram law of addition, I am going to get something like this as my resultant. The resultant is going to be along this axis. So this will be 30 degrees and this will also be 30 degrees. So I will have root 3 divided by 2 Im cos 30 plus root 3 divided by 2 Im cos 30. And cos 30 is root 3 by 2. So I'm going to have 3 divided by 2 n times Im. If I take the number of turns also into account, I should write n everywhere. So this is going to be 3 by 2 n Im. So if you look at the magnitude, it is same as what we got at t equal to t0. Now at t equal to t1 also we are getting the same thing. But if you look at the angle, this is theta equal to 30 degrees. So from theta equal to 0 degree position, the same 3 by 2 n times Im flux vector or MMF magnetomotive force vector has moved by 30 degrees. So when the omega t has traversed from T0 to T1, which is 30 degree duration, this has also traversed 30 degree duration in anti-clockwise direction. Now let us look at what happens at t equal to T2. So let me try to draw that clearly. At t equal to T2, so at t equal to T2, what is going to happen is you can see very clearly that these two are at 30 degree point, or from 0 crossing, this is 30 degree away. From this 0 crossing, this is 30 degree away. So both these are going to be something like Im divided by 2 because sine 30 is half. Whereas at this point, we are going to have our IC to be peak value. So this is going to be peak value, which is Im, but it is going to be negative peak, so minus Im. So let me write this as Ia equal to Im divided by 2. IB is also equal to Im divided by 2. And IC is minus Im. Whatever we saw here, that's what I'm writing. Okay. Now, correspondingly, let us draw. As far as A phase is concerned, it is just Im divided by 2. And if I look at B phase is at 120 degrees. It is 120 degrees away. So I should have this as B phase. So this will be N times Im divided by 2, which is Fa. And this will be N times Im divided by 2, which is Fb. And Fc is along this. Already whatever we have written, the same thing holds good. So Fc has to be along this with Im. So it is the same situation, very, very similar to what we saw in t equal to t naught. It is not any different. Only thing is at t equal to t naught, the maximum NIM was remaining along theta equal to 0. Whereas here n times Im, which is corresponding to Fc, that is remaining along theta equal to 60 degrees. So this is 60 degrees. This is 60 degrees. So when I vectorially add this, I should have ultimately the resultant vector to be along this with 3 by 2 times Im. So I should say F resultant is going to be n times Im plus n times Im by 2 multiplied by cos 60, which is corresponding to Fb, and n times Im divided by 2 times cos 60, which is going to be Fa, this is Fb, and this is going to be Fc. So again, what we get is 3 by 2 times NIM. But this is along theta equal to 60 degrees. So originally it was at theta equal to 0. The next time it became theta equal to 30. Now it has become theta equal to 60. So when omega t kind of, moved away from t naught by 60 degrees, this vector has also moved by 60 degrees in anti-clockwise direction. So by extension, we should be able to say for every 30-degree displacement of this omega t, the vector is going to go round further and further in the anti-clockwise direction by 30 degrees. So when I have one cycle of sinusoid completed, in all probability, the revolving vector, the magnetic field vector, would have started from here and it would have gone round like this and it would have come back to the same position from 0 degree to 360 degrees as far as omega t is concerned. If omega t has traversed one cycle, at the same time, the resultant flux is, it would have actually traversed 360-degree rotation completely along the stator's cross section. So I can say the revolutions per second, what I see, revolutions per second is equal to, I should say, whatever is the frequency of the input current. So if I have a 50 hertz current, I am going to have, so if frequency is equal to 50 hertz, then revolutions per second is going to be equal to 50. So revolutions per minute, RPM, is going to be 50 multiplied by 60, which will come out to be 3000 RPM. Okay. If I want to express it in terms of angular velocity or radians per second, so I should say 2 pi radians are traversed, right, in 1 by 50 seconds. Or I should say in 1 second, 2 pi multiplied by 50 or 2 pi f radians are traversed. Or indirectly, I can say if I want angular velocity omega, that should be given as 2 pi f. This is the velocity in radians per second. So we call this as angular velocity or rotational velocity. So the revolving magnetic field theory states that if I am going to supply three-phase space distributed winding with three-phase time distributed sinusoidal currents, then I am going to have a magnetic field of constant magnitude, which is corresponding to 3 by 2 times peak current multiplied by the number of turns. This is going to be the magnetomotive force that is manifested by the three-phase sinusoidal current supplied to three-phase space distributed winding. And this was a brilliant discovery that was done by Tesla. He kind of predicted that if you try to supply a three-phase space distributed winding with three-phase time distributed sinusoidal currents, it will create a revolving magnetic field, and that can be a very nice motor which can, be self-starting, which will be able to give, a continuous rotation without any vibrations, without any kind of jerky motion and things like that. Now, if rather than having only one A and one A dash, so let us say I have A here, and let us say I have A dash here, and I'm going to have A1 here, and I'm going to have A1 dash here. Okay, so if I am going to have basically a winding like this, and similarly, I want to have B exactly 120 degrees away, rather than that, instead of having now A and A dash by 180 degrees away, I have had them only 90 degrees away. So all the angles I have divided by 2. So instead of having B at 120 degrees away or C at 120 degrees away, I'm going to have C at this point. So this is going to be C. Okay. So I should have one more C1 here. So this is C and this is C1. And I should have actually correspondingly C dash, and I should have C1 dash here. Okay. So I have drawn it somewhat like this. And if you look at the two-pole winding, what we had shown earlier, B was shifted from here by um, 120 degrees. So I should show B, which is actually sitting from here. So C1 dash I should have shown here. So this, 1 second. So let me show this somewhat like this. So I'm going to have on this side, if I draw B here, this is going to be B, and I should have so this is going to be C1 dash. So I should have one more B, which is actually the return path somewhere here. And similarly, I should have one more B somewhere here and one more B here. So this must have been B, and this should be B dash, and this should be B1, and this should be B1 dash, and so on. So you can very clearly see that what is considered as 90 degrees as far as the mechanical rotation is concerned, that is corresponding to complete current reversal, which corresponds to actually 180 degrees as far as electrically concerned. So if there are 2A and 2A dash, that is, this is forward current and this is return current. Then mechanical angle of 90 degrees is equal to electrically complete current reversal. So electrical angle of 180 degrees. So I can say electrical angle divided by 2 in this particular case. So here, if I have so many number of windings, 4 windings, the previous one corresponded to only A and A dash. So when you have only one pair of forward and return path together, you call that as two-pole winding. So this is essentially, it will create only two poles, one north and one south pole. It looks as though that is rotating at 3000 RPM if I am supplying these windings with 50 Hertz. Whereas in this particular case, I will be supplying A and A1 with forward current of A phase, A dash as well as A1 dash with return current of A phase. So this corresponds to 4-pole winding. If I am going to have A1, A2 and A dash, A1 dash, A2 dash, that will correspond to 6-pole winding. If I am going to have A1, A2 and A dash, A1 dash and A2 dash, that is going to correspond to 6-pole winding. So electrical angle divided by P by 2 is going to be equal to mechanical angle. If the number of poles is only 2, then electrical angle and mechanical angle are going to be one and the same. If the number of poles is 4, in that case I have to divide the electrical angle by 2 to actually get what is the mechanical angle. So what I'm trying to get at is, by the time electrically the current reverses completely in a 4-pole winding, the actual movement that has taken place is only 90 degrees. So the number of poles, as it increases, the speed at which the revolving magnetic field rotates, that is going to be lower and lower. So this is a very, very important factor. As the number of poles increases, then the revolution speed, the speed of revolution of the magnetic field decreases. And if I want a low speed machine, that's why I will have more number of poles in my machine. And if I want a high speed machine, the maximum I can obtain from 50 Hertz is only 3000 RPM, nothing more than that. Okay. And one more thing I would like to specify is, if I am actually looking at A phase winding supplied with A phase winding supplied with A phase current, B phase winding supplied with B phase current, and C phase winding supplied with C phase current, my revolving magnetic field is rotating in anti-clockwise direction. Instead, if I had given B phase winding supplied with C phase current and C phase winding supplied with B phase current, it would have actually seen completely the rotation coming in the opposite direction. You would have seen that whatever I have shown as FC, that would have become FB. So I would have got that somewhere here. So the rotation would have taken place in the anti-clockwise direction. So by only interchanging two phase currents, IA you leave it as it is, but IB and IC you are going to interchange. IB is going to be given to C phase winding and IC is going to be given to B phase winding. In that case, you will see a reverse rotation. So we should be able to say that for reversing the direction of rotation, interchange only two phases, two phase currents. So what I mean is you may have IA being retained as it is, but IB should be given to C phase winding and IC should be given to B phase winding. So you can do that instead. IC can be retained in the same way, whereas IB should be given A phase current and IA should be given to B phase winding. That can also happen. So one phase has to be retained as it is, and the other two phases are to be interchanged with each other. That will automatically make the direction of rotation reverse. Okay. Now let us try to look at basic principle of operation of synchronous motor first. So what is the principle of operation of synchronous motor? So as I mentioned earlier, in both synchronous motor and induction motor, three-phase case, you are going to have three-phase distributed winding somewhat like this. So I have A phase winding here. I'm going to just switch back to two phase winding only, two pole winding only. So that way it is much simpler. So this is going to be A dash, and this is going to be B and B dash. And I'm going to have C and C dash here. Now, as far as the rotor, especially in a permanent magnet synchronous motor is concerned, it is going to have permanent magnets here. So I'm going to just show it as though this is the magnet. So this is going to be North Pole and this is going to be South Pole. Let's see. So when I am actually exciting the three-phase windings in the stator with three-phase time distributed current, we said that it is going to create a revolving magnetic field, which is rotating in, say, anti-clockwise direction. And let's say at this instant, it is as good as having a magnet which is probably having South Pole here and North Pole here at this juncture. It is going to be South Pole here and North Pole here at this juncture in the air gap. So what is going to happen is the rotor will be dragged by this South Pole because of the attraction force. So this is created by the stator winding currents. It is a revolving magnetic field and it is created by the stator winding currents. Whereas this is the rotor magnet. So the rotor magnet is going to be dragged along by this stator revolving magnetic field. Now, we can have this permanent magnet in two different ways. I can actually have it as though if I'm going to have the rotor magnet somewhat like this, let us say it is completely, it is a complete rotor somewhat like this, and I'm going to mount this magnet on the surface here. So I call this as North Pole. And I mount this magnet on the surface here. So This is all made up of ferromagnetic material. Only on the top, I'm going to glue the magnet with some resin or something like that. So this is North Pole and this is South Pole. And once this South Pole is appearing here because of the stator winding current, this North Pole is going to be dragged along and this is going to go round and round if it is able to lock up with the stator revolving magnetic field. When you put the magnet like this on the top, we call that as surface mounted PMSM, surface mounted permanent magnet synchronous motor. Rather than that, I may have actually, this is, let us say, my stator, and my rotor can be somewhat like this. It can be a buried magnet, and I can have something like this. So the magnet can be buried somewhere here. This could be North Pole, and similarly I can have the magnet buried here, which could be South Pole. So this is interior permanent magnet machine. And what is going to happen is, if you look at the magnetic material has large reluctance normally, which is equal to reluctance of air. That is, it is not going to allow the magnetic field lines to pass very easily. So even if I am having a structure which is almost like cylindrical in nature, like this is cylindrical in nature, the rotor as well as stator, they are cylindrical, they are like concentric cylinders. So here also the stator cylinder is like this, whereas the rotor cylinder, if I say this is the rotor cylinder, which is concentric, I have not shown it exactly like that. And I'm going to have the North Pole buried here and South Pole buried here. This is the permanent magnet pole that is buried here. Now, because I am going to have here between stator and rotor, the air gap is uniform. The air gap is completely uniform in surface mounted machine. Whereas if you try to look at it here, this is going to again give me more amount of reluctance compared to what happens along this. So this axis is going to give more amount of reluctance as compared to this. So we call generally the axis along the magnet as direct axis or D axis. So here also I can say this is D axis. And Q axis is exactly perpendicular to that. So Q axis does not have the magnet coming in between, whereas D axis has magnet coming in between, assuming that all these portions are going to be ferromagnetic material. D axis has more reluctance compared to Q axis reluctance. So reluctance and inductance are exactly, inversely related with each other. So I should say in this particular case, LD, direct axis inductance, when a winding is coming along the direct axis, it is going to manifest less amount of inductance as compared to when it is along the quadrature axis. So winding when it is close to the direct axis will have higher inductance, lower inductance as compared to when it is coming close to the quadrature axis. This is what happens in the case of a permanent magnet synchronous motor where the magnet is buried. So this is generally known as interior permanent magnet synchronous motor. So there are mainly two kinds of synchronous motors we see: surface mounted and surface mounted permanent magnet synchronous motor. So surface mounted and interior. And in the case of interior permanent magnet machine, very clearly, even at very high speeds, these permanent magnets, because they are buried, they are not going to be thrown out. Whereas in surface mounted machine, because they are on the surface, they can be thrown out. It can be really detrimental to the machine. So this is mechanically not that rugged. Whereas this is interior permanent magnet is generally very stable and rugged. And there are, because of which the speed range can be very, very high. The range of speed for interior permanent magnet machine is high. And one more thing we can say is efficiency wise, generally, these are going to be better. Efficiency is generally better in IPM SM. That is one reason why only this is used in electric vehicles. In electric vehicles, normally you see only interior permanent magnet machines being used. Coming back to the principle of operation of the synchronous machine, what we see normally in the case of a synchronous machine is, let us say I have the stator here, and because the three-phase windings sitting here are fed with three-phase time distributed currents. So let us say this is A dash, this is B, this is B dash, and this is going to be C and C dash. Okay. So because of which we are going to create a revolving magnetic field somewhat like this. And if I have the magnet, which is maybe something like this, which is currently, this is, let us say, North Pole and this is South Pole. And your revolving magnetic field has, let us say, North Pole somewhere here and South Pole somewhere here. So this is going to be attracted. The North Pole of the rotor is going to be attracted towards the South Pole created by the stator winding current. So if the rotor is already up and running, it would be able to lock up with whatever is your stator revolving magnetic fields pole. But if the rotor is starting from zero speed, but already the stator revolving magnetic field is rotating at a very high speed like 3000 RPM, this North Pole will slowly try to move towards South Pole, but by the time it just makes up its mind and locks up with South Pole, by then already this North Pole would have reached the other side. Then it will see repulsion. So you would see alternately attraction and repulsion until really you give a kind of a jump start to the rotor and bring it closer to 3000 RPM. So alternately, attraction and repulsion will be faced by the rotor, because of which you would see only some kind of dwindling movement, some kind of vibration you will see in the rotor. So that is one reason why synchronous motors are normally not self-starting. They are not going to start on their own. Whereas you will see that in induction machine, they start on their own. Synchronous motors are not self-starting. If at all you want to make them start properly, you might have to start with 0.5 hertz or 0.25 hertz or something. A small supply frequency you will give, which means it is going to rotate at 15 RPM or 10 RPM. So hopefully the rotor will be able to catch up with this. Then after that, you slowly increase it to 0.5 hertz. So it goes to 20 RPM, rotor will be able to catch up step by step. Then you go to 1 hertz, 1.5 hertz, 2 hertz, 3 hertz, and so on, and then increase it slowly to 50 hertz or whatever. So this is generally known as variable frequency starting. And in the case of an electric vehicle, anyway, the source is a battery, that is a DC source, that will be converted into AC with the help of an inverter. So you are going to have, let us say, a battery, and after that you are going to have the DC to DC converter, because the inverter input voltage and battery voltage may not exactly be matched with each other. So the matching is generally done by a DC to DC converter. This DC to DC converter's output, which is now stepped up or stepped down to the level required by the inverter. So the inverter input now is at appropriate level. Now that is going to be connected to the three-phase machine, whether it is induction motor or synchronous motor. And that will be coupled to the wheel, that is coupled to the load. Okay, so when you do this, you can definitely increase the frequency slowly for the inverter, and you can allow the motor to pick up speed or in its own pace. It can go pretty slowly, and then it can catch up with whatever is the speed of your revolving magnetic field at every step. So slowly you can change from 0.25 to 0.5 hertz to 1 hertz and so on. So that will happen quite smoothly, quite nicely in an electric vehicle. That's not a problem. Okay. Whereas in an induction motor, if I try to look at the induction motor's operation. So what happens in an induction motor is, I have the stator winding, which is sitting here. Again, that is going to be A dash, B dash, and C dash. So this is the way it is going to be. So let us say this is dot, this is cross, and this is going to be A dash. This is going to be B, and this is B dash. And this is going to be C, and this is C dash. Now this creates a revolving magnetic field here. As far as the rotor is concerned, it is just going to have three-phase windings, somewhat like this, which are also distributed winding, and I'm going to short circuit them externally. So when the three-phase rotor contains windings and they are short circuited externally, we call this as wound rotor. But most of the times what we use in many of the applications where they have to be completely maintenance free, we call the rotor as squirrel cage rotor. It is going to be squirrel cage rotor. So the squirrel cage rotor structure is somewhat like this. You are going to have, let us say this is the cage that you are making. This is one rotor conductor. This is the second rotor conductor. This is the third rotor conductor. This is the fourth rotor conductor. Like this, I'm going to have multiple rotor conductors all over. And they are all going to be short circuited on both sides with two end rings. So this is going to be one end ring, and this is going to be the other end ring. This is how they are going to be short circuited. So we call this as end ring, and we call this as conductors, rotor conductors. And if you look at this, it is looking like a cage. That's why we call this as a cage rotor. And if your looking at the backside of squirrel, it is going to have these kinds of lines. That is the reason we call this a squirrel cage rotor. In squirrel cage rotor, it's very difficult to differentiate between whether this conductor belongs to A phase or B phase or C phase. Whereas here you will be able to say this is probably A phase rotor conductor, this is B phase rotor conductor, and this is C phase rotor conductor. So what happens in the rotor is I am going to have rotor also having slots at the outer periphery like this. So I'm going to have rotor slots. Let me draw this completely. So this is going to be the rotor slots which are carved at the outer periphery of the rotor. Now, I am going to have one rotor bar here, whatever I have shown, rotor conductors or rotor bar, because they are going to be really thick. I'm going to have another one here, and so on. So I'm going to have multiple number of rotor conductors or rotor bars, and they are going to be short circuited with the help of end ring on both the sides, and they are all welded or braced together. So that way, you are not going to be able to separate A phase conductor, B phase conductor, and C phase conductor. Neither are you going to say that this particular conductor carries A phase current or B phase current or C phase current. So one major advantage we see with respect to the cage rotor is it is adjustable or adaptable for any number of poles or any number of phases. So if I have a single phase induction motor and I'm taking the rotor out of a single phase induction motor and place it into three phase machine, it will still work. As long as it can carry that much of current, it will still work. I can remove a cage rotor from a 4-pole machine. I can put it into 2-pole machine. Still, it will work as long as it can carry that much of current. So that way, squirrel cage rotor is really adaptable or flexible. And it is also maintenance free, because you are not going to see that here you have to externally short circuit the three-phase conductors in a wound rotor, whereas here it is internally short-circuited, so you don't have any kind of moving parts within the rotor structure itself. The rotor as a whole might move, but you will not see any moving parts within the rotor. Now, coming back to the principle of operation, if I have a revolving magnetic field like this, as I told you, it is as good as having a north pole on one side and south pole on the other side, and continuously rotating that at 3000 RPM or something like that. Now I have the rotor conductors which are short circuited with the help of end ring that is placed within the inside of the stator. Now, the rotor conductors are on the surface of the rotor. They are going to look at this magnetic field. So what they visualize is a varying magnetic field. Sometimes they will see south pole, sometimes they will see north pole, sometimes they will see a magnetic field of lower strength, sometimes they will see a magnetic field of zero strength. So the rotor conductors visualize a d phi by dt, rate of change of magnetic field. The flux value depends upon how much is the stator current and how much is the stator conductors, how many number of stator conductors I have. But how much is the rate of change of flux, that is dependent upon what is the kind of speed at which the revolving magnetic field is rotating. So the speed decides what is the kind of rate of change the rotor conductors are visualizing. So higher the speed of the revolving magnetic field, or higher the speed difference between the revolving magnetic field and the rotor conductors, you are going to see more and more induced EMF. So whatever is the speed of the stator revolving magnetic field, whatever is the rotor velocity, these two have to be subtracted from each other. So this is the relative velocity that is going to decide how much is really the induced EMF, apart from the magnitude of the induced magnetic field itself. So when the rotor is in stationary condition and there is a revolving magnetic field which is rotating at 3000 rpm, for example, for a 2-pole 50 hertz machine, the rotor conductors are going to see a huge d phi by dt. So with Faraday's, as per Faraday's law, there will be an induced EMF in the rotor conductors. So if there is an induced EMF in the rotor conductors and it is short circuited already, there will be current in the rotor conductors. There will be a circulating current in the rotor conductors. If there is a circulating current, especially 3-phase in the rotor conductor, then I'm going to have definitely a magnetic field, a revolving magnetic field, a revolving magnetic field is produced by the rotor currents also. So what is going to happen is there will be an interaction between, so if I call this as psi r, and if I say the revolving magnetic field what has been created is psi s, so interaction between psi s and psi r, this creates a torque, electromagnetic torque. And as per Lenz's law, this electromagnetic torque is going to work in such a way that it reduces or it tries to make its own root cause disappear. And the root cause is, as I told you, the relative velocity between the stator revolving magnetic field and the rotor velocity itself. If the rotor tries to catch up with the stator revolving magnetic field, and if the speed of the rotor also becomes omega s, same as the stator revolving magnetic field, then it will not see the north pole or south pole changing positions continuously. As long as it is locking up with exactly the velocity of the stator revolving magnetic field, it will not see any rate of change of magnetic flux at all. So d phi by dt will become 0 if omega s and omega r, the revolving magnetic field speed of the stator and the actual rotor velocity, if both are equal to each other. So the electromagnetic torque would try to rotate the rotor in the same direction as that of the revolving magnetic field created by the stator, and it will try to push it to omega s. So if the rotor achieves the speed of omega s, then d phi by dt will be 0. If that happens, then no rotor induced EMF, no rotor current, no torque. So ultimately, at that point, immediately it will try to fall back into, fall back in terms of its speed. So if the speed decreases, then again there will be rotor induced EMF, there will be rotor current, and there will be a small amount of torque. So ultimately, omega r will settle at a speed slightly less than omega s, such that there is a small current, there is a small d phi by dt, there will be a small rotor current. And psi r, and there is a small torque that is produced so that the rotation can be sustained. So the induction motor basically works on the principle that as long as there is at least a small relative velocity between the revolving magnetic field of the stator and the actual physical rotation of the rotor, there will be a small induced EMF in the rotor circuit, which will cause the current to flow. There will be a rotor flux, and the rotor flux will interact with the stator flux to create a small torque that will sustain the rotation. So induction motor, by its own principle, you can see very well that it will be a self-starting motor as compared to what you see in the case of synchronous machine. But only problem is, in permanent magnet synchronous machine, you have magnetic field available from the rotor side also. Whereas here, the rotor gets a flux only because of induction. So obviously, we will have some kind of limitation in terms of how much will be the current required to create the flux in both stator and rotor, and how much can be the air gap between the stator and rotor. If the air gap is larger, it will draw larger current to create a good amount of flux in the stator as well as rotor. So from that viewpoint, induction motor cannot be as efficient as synchronous motor is. So we'll continue with this induction motor operation in the next class.